So we are talking about leave one out cross-validation. So we have, as the name suggests, we'll just leave only one element out for testing. Other than that, we'll use all the things for the learning model. So for with the first iteration, we leave one out and 2, 3, 4 till n. We use it in training. Now the second time, we took 2 as the testing and 1, 3, 4, and 5 and all as training. The same thing we did for all the iterations. So it now what the problem with this thing is, if you have 10 million data set, it's going to go for a iteration of 10 million times. So that is not computationally good. It means you can't even do that computationally now on, because doing an iteration 10 million times is not feasible for your machine. So we don't use leave one out cross validation now. But just to let you know what is leave one out cross validation, we just take one element as a testing. Other than that, we take all the elements as training. So that is leave one out. Now the one which we got new is k-fold cross validation. What we do for k-fold cross validation is, instead of taking only one element, we make folds of the data. Just imagine, as the name suggests, it's k-fold cross validation. So we have to find the number of k. Depends on you how many types of, like, what is the value of k you want. It can be 5, 10, 15, 20, or whatever. So just imagine k as value as 5. Okay, and imagine the whole training data, you have 1000 elements. You have 1000 elements and you made the k as 5. It means you're telling the machine that out of this whole 1000 data sets, divide it into 5 folds. So 1000 divided by 5 will be 200. So each and every box will be a 200. Yes, bro. Each and every one will be a 200 set data, as you can see. So we have k-fold cross-validation. We give k as 5. Now what we'll do is, for the first iteration, we'll take the very first fold as a training data, as a testing data, and other blue what the blue folds as a testing data. Sorry, the training data. So we can see we trained it on the second, third, fourth, and fifth fold, and we tried it on the testing is done on the green one. Now for the second iteration, the first, third, fourth, and fifth are used for the training. The second one is gone for the testing. Similarly, we'll do it for the number of iterations that we gave. So that is k-fold cross-validation. Now it sounds completely fine. The cross-validation is completely fine in this one, but there can be one slight disadvantage for this cross-validation. The only problem can be, there can be a chance like you started splitting the data into folds. You took the very first validation. Like there can be a chance like when you split the data and you took the very first fold as the testing data, again the problem which is there in training test split, it can happen here also, that you have, like, just think you have 1000 data sets. On the very first 200 data set, you only have the answer of yes, 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 yes. That can happen. Like you cannot control like what kind of data, like on the data set, how they are placed. They can be like, out of 100 data set, the very first 500 data set stands for yes, the next 500 data set stands for no. That can happen. So if we'll do this k-fold cross validation there, it can be a bit biased, because the validation is only happening on one type of answer. There are only one type of data set in the validation sector. And when you go for the last iteration, you'll only get the other type of variation as the testing data. That's one of the smallest disadvantage of k-fold cross validation. So just to overcome that cross validation problem, we made one more, which is where it gone. Stratified k-fold cross validation. Now what we do in stratified k-fold cross validation is, first we try to find out what is the distribution of the answer. Like with guessing yes and no, it try to figure out what is the percentage of yes and no. Like in the whole data set, if the 40% of the answer is yes and 60% of the answer is no, so it will exactly do the same thing. It will divide the set into 5 number of folds only, as this is known as stratified k-fold cross validation. So it will stratify. The k-fold validation is going to happen, but the stratify is that it will divide the state. It will divide the data. See, like what the percentage of yes and no answers are there. What are the percentage of the outputs are there, and it will make sure for each and every fold the percentage of answer should be similar. As you found out, that in the whole data set you have 40% of yes value, 60% of no value. So it will make sure that the data set that they make, the folds that they make will have 40% of yes and 60% of no value. This will make sure. So it will make a uniformity in between all the validation and the training data set, so that the problem that you occurred in the cross validation, the key-fold cross validation, that one of the fold can have only similar kind of data, that will not happen in stratified key-fold cross validation. That is everything about cross validation. Now, where are we going to use the cross validation? For that, like cross validation is one of the really good things, but why we use it? To make cross, as I told you, the cross validation is really helpful when you go for like the average accuracy. As when you do the train test split, you can have like oscillating accuracy, because depending upon what random state you got, the accuracy can change. So why we use, for that reason we use cross validation. Now, that other two things which I want to tell you is ridge regression and lasso regression. Now, as I told you, linear regression. I guess you remember about linear regressions. What I told you, that we make a straight line or the data points that we try to find out, and how we make the straight line. We use the cost function, which is like the distance of the actual point to the predicted point. We make it a square and then start adding it to all the points. That's the cost function, which I explained to you already, and we try to minimize it. That's how linear regression works. What does regression work? Ridge regression, what it does is, so what a regression will do, there can be a chance like your data will overfit. Like you provide a less amount of data. You provided a less amount of data. So the data, your model will go in overfitting. Like it will completely accurate for the training data. But when you're trying for the testing data, it can have like random results. So what will happen is, what will regression will do? It will change its cost function a bit. So as you can see, arg minimum, we are trying to minimize the cost function sigma of yi, which is the actual value, minus bixi. It means the predicted value that I'm getting from the regression line. We are squaring it and adding it. So that's the similar cost function that we have in simple integration. We have one more extra thing, which is called as delta of summation of b square. Now beta stands for the slopes. As you can tell, ridge regression will do exactly one thing, and that it will put some penalty on the slopes of the line. So if the line, like for small value of changing in x, there's a huge spike change of y, ridge regression will do a penalty on that. Like you cannot change the value of x, you cannot change the value of y way too large in a small change of x. So that's ridge regression. How it does is, it will add this particular term, which is alpha of summation of beta square, which is for each and every point, like you make the line y is equal to mx plus c, or for in simple lines, in simple words, if I use the multiple integration, y is equal to m1x plus m2x plus m3x plus c. So in argument minimum, what we'll do, the y actual minus y predict, squaring it and adding it. What more it will take? It will take the slope of each and every attribute, like m1x to m2x and m3x. It will take m1, m2, and m3, square it, and then add it, and then multiply it with a number, a tuning parameter, which is sigma. How sigma is calculated, I'll teach you like in 5 minutes how sigma is calculated. Sigma is just like a Haber parameter which we decide. Now what is so that's how regression works. It will also take care of what overfitting that you're providing the. It will take the slope and then give you the cost function. There can be a chance like the data is overfitted, completely overfitting that. So it will give you a 0 answer for the linear cost function for linear regressions. So for this one, you'll get a 0 answer because it's completely overfitting on the training data. So this particular term will be 0. But because the slope is really high for that particular training data, for that particular line, it will give a small error here that your slope is really high. So it will try to, like, this is the line, it will try to bend the line a bit to make it more generalized. That's what regression will do, because it's trying to tamper, like penalize the high slope data. So as you can see, what I told you in what is that called? simple linear regression or multiple linear regression, we try to minimize the cost function. This is already 0, but we got some value in this. So the machine will try to minimize the whole functions, so that even if this, just imagine this given this answer as 0 and this answer we got as 5. So the whole cost function came as 5. But now increasing this a bit, like increasing this to 0.1, but we can decrease this particular value to 2.5. We got this error as like the normal normal linear error as 0.1 or 0.2. But because increasing a bit of error in the normal data, we got cost function decrease because of the decreasing slope. So we can imagine, like, because we increased a bit of errors in this, so that instead of 0, now it's giving an error of 2.5, the error of 0.5. But increasing the error here, it means the reducing the error here. So from 5, it can come to 2.5. So the total can be, don't do it, please. So instead of doing with that, we can decrease the cost function. So that is what regression will do, to just penalize the data, penalize the slope. Now, the lasso will exactly do the same thing, but it has a change in the function. Instead of, as you can see, the cost function of lasso, the whole data set is the whole cost function is exactly the same, but the only change is, instead of squaring the what is it called? Instead of squaring, I got a message. Where is beta? Okay. You'll get to me. The beta and the beta are the slopes, as I told you in the last also. They are the slopes for the line that you make. I'll show you in Rich. Beta is the slope of the line, that y is equal to mx plus c, or y is equal to m1x to m2x to m3x. The m is the beta. In this particular formula, it's represented as beta. It is the slope of line. So what will Lasso do it? Lasso will have the same, sorry, not low CV, Lasso. Lasso will have the same, as W. I don't know, I didn't get proper picture. It's represented as W. So instead of squaring the slope, what it will do, it will just magnitude the slope and start adding it, and it will do the exact same thing. The normal cost function of the simple or linear regression, and it will add this particular cost function by itself, addition of the magnitude of the slopes, and multiplying it with the alpha or beta, or what, like lambda that I showed in the previous example. Now, how we find the lambda is which I'm going to teach you later. Now, this is Lasso regression. Both does exactly the same thing, but they do it in a different way. Lasso also penalize, Rich also penalize the high slope, and Lasso also penalize the really high slope. It will try to bend the line towards 0. Now, what was the one advantage of Lasso is, Lasso will try to bend the line towards 0. Both are like trying to bend the line towards 0, like x to 0. But Ridge will not completely try to bend the line towards 0, but Lasso will, because we are not in Ridge. We have a square function, so it will not bend the line totally. It try to bend. It will not completely make it completely parallel. Lasso can do that because we're directly using the magnitude. So there can be chance, like when you're doing carrying out this function, there can be chance like there are like 1 or 2 elements for which the magnitude it made the magnitude completely 0. So with that, Lasso helps in feature selection. Like for linear regression, you found out that for a linear regression, y is equal to m1x plus m2x. Just imagine for m3, we got a slope as 0.1. It's not really significant, but when you did the lasso, it can happen that 0.1 will be completely reduced to 0. So it can have lasso can do one thing to increase the accuracy. It can remove some of the features that you provided, so that you're functionally simplified and it can give more accurate results. Because if the feature will have really less impact on the answer, it will try to remove it. That's what Lasso has something different with the Ridge. Other than that, exactly do the same thing, but the only thing is difference is the exact cost function. There they have a square function. Here we have a magnitude function. Now we'll see how it's working in the code. So now from Sklearn dataset, we load the Boston dataset. There are like so many dataset which is already present in the Sklearn library. So we use the Boston dataset. So Boston dataset is loaded. Now NumPy, Pandas, Matplotlib, and Sklearn. These four are the things which we use all the time. As I told you so many times, NumPy, Pandas, Matplotlib, just to plot the lines, it's gonna be there. Matplotlib, we're not gonna use it right now because this, the example that we're gonna take is multiple linear regression, and we cannot plot the graph for multiple linear regression unless we have 3 parameters. Then it's possible to plot the graph because we can have a 3D graph, but more than that we cannot. So that's why we're not going to use any Matplotlib. So we loaded the load.boston. Let's execute. That's going to take a bit of time because I just started it. Now, the data set that you'll get will not be like a proper data frame. It will be scattered. Not a scattered, like it will be in like array structure as I showed. Let's hope it comes back fast. No. Oh, sorry. So now the data set has the data. So the data set had the data and the target, as you can see. It is all the data. It is the target, the answer key, and now how to make it? How to make it in a proper data frame. Now we use the df.data and we put it into the data set by using pd.dataframe. Now then we printed the data set out, print the data set head. Data set head will do what? The very first 5 rows it will print. So the very first rows, as you can see, I wanted to very first 5 row, you can see you got all the data. Now I have to provide the name. Like you can see the columns are 0, 1, 2, and 3, and 4, and 5. But we know what other features are because it's given in the data set. Feature name that array. So we'll do what dataset.columns is equal to df.feature. So the dataset feature name will be provided as the datasets column. So now we'll print the dataset again. We'll get the columns name here, crim, zn, index, whatever. Now what we do, we make one more column here, which is df.price, and we provide the target data, and we print it again. So crim, zn, index, and whatever. And at last we'll get one more row, which is the price, which is the r, which is our y, which we're gonna guess. Now what we do is we make the data set as y, which is our training data, which is our like on the data we're gonna train, which is the dependent variables, and what will be the y, sorry, the independent variables, what will be the y, which is the dependent variable. So we written x and y. So data set of file of all number, you can see there's no number, which means all number of rows. So from 0 to whatever number of rows, starting from 0 till -1. So till -1, it means it will leave the -1. The minus stands for the last row, last column. So before -1, it will take all the values. So till lstat, it will take all the values in x. Dataset y, which will be the price column, because it has all number of rows and only the -1 column. So it is a dependent feature. Y is equal to mx plus c. We got our y, we got our x. Now we're going to use what? Linear regression function. We declare the linear regression and the cross-validation score. Now the cross-validation score, which I told you just before that, how to use the cross-validation score. In Sklearn model selection, we have a function called cross-validation score. Now what we do is, first we make a linear regression script, as I showed you in the linear regression classes also. What we do is, we try to find the mean squared error using the cross-validation. Cross-validation will take, like as I told you, cross-validation, the key for cross-validation do what? Split the data into so many folds and it will give you the mean of that. Like for each and every k iterations, it will give you the mean squared error. So for cross-validation, we provided the linear regression function where we want to try to do it on. We provided the, if you'll see the exact name, what is called, it is called as, I didn't do it. Okay, sorry. I should have executed all the functions till now. We'll go to cross-validation score. Now the first thing you do give is the estimator. What is estimator is? It will give, you'll have to give the exact algorithm which you're trying to use. Either it's going to be linear regression, support vector matrices, or random forest decision trees, whatever. So you have to provide the estimator on which model you're trying to do the cross validation. We provide the x value and the y value, and scoring. In scoring, we'll try to tell that which output on which output you're going to test it on. Whether it's going to be mean squared error, as if for this it's mean squared error. You can have mean absolute error or root mean square error, as many times here, and CV cross validation number. This time we're providing number of cross validation we're going to, as in K for cross validation. The K stands for the number of cross validation. So it's 5. So what it'll do, it'll take the whole data set and it'll try to divide it on 5 and it'll do the cross validation stuff. Now the whole line will give an array, sorry, a list. For each iteration, what is the mean squared error that you got? The mean squared error that you got for each iteration. We saved it in this. No, we saved it in MSC. Now what we did is we take the mean of all the errors, like for 85, 86, 87, 87, or whatever error you got. We made the mean of that, and we printed it. So the mean that we got for this model is minus 37.13. As I told you, as close as the mean squared error is to the number 0, the more accurate it is. So for any model which you're trying to make, if your mean squared error is really close to 0, it's a good model. If it's going far from 0, it's deteriorating. So to make this thing more accurate, what we do is we try to bring this particular number minus 37.1 close to 0, because it will come close to 0, it will be more accurate. Now we use the linear regression. We can use the ridge regression now. From similar again, from Sklearn that linear model, import ridge. Now we can use one more thing to try to tune the hyperparameters, but the meeting time is only 5 minutes, so I'm explaining you the ridge one and the hyperparameters. I wanted to join again, so that I'll teach you just 5 minutes more of Lasso. So what does grid search CV do? As I'll tell you, grid search, as I told you, you will have so much of parameters available for ridge. As I'll show you, where is grid search CV? Shift enter, it should work, but okay, let's execute this. Now the estimator, param grid, or all this parameters that you can use for each and every function, like ridge, linear regression. I'll show you linear regression also. Where is linear regression? Okay, I'll show for cross validation also. Like so many parameters that you can use. We don't use it generally. We give only the default values and let it happen. So it can happen that the hyperparameter that you have, only a small tweak can make your model more accurate. But how to describe, like how to find out which hyperparameter we should change, which hyperparameter we should put to have the best accurate results, for which we use the grid search CV. What will grid search CV will do, as you'll find in ridge, if ridge will have, if you can provide this much of hyperparameters for ridge, the alpha value, the fit intercept, the normalize, the copy, max iteration, total, solver, random set. So for each and everything, you have no idea what you should put to get the best out of your model. For this particular function, for this particular problem, we use the grid search CV. What will grid search CV will do? Grid search CV will take the input of the parameter. First, we'll take the estimator, which is the ridge function, and it will take the parameters. Like out of all the parameters that you can provide in ridge, as you can see, the parameter you can provide in alpha, fit, and now we want to try in different number of alphas, that which one will fit properly. So we made a parameter which is a dictionary in which the key will be the exact parameter that you're going to try out, and the value will be all the parameters which you're going to test it on, like 1 e to the power minus 15, 1 e to the power minus 10, 1 e to the power minus 8, like really small values. It can go to 5, 10, 20, 30, 20, 100, whatever. Now what will grid search CV will do? It will take the estimator, which is ridge, the parameters, like what all alphas in which you're going to try on. Now the scoring. Again, the scoring which you provide, the mean squared error. Like for each and every value of alpha, it will try to find the mean squared error, and it will give you back the mean squared, the best one, and try the k-fold cross validation 5 times. Like as I told you, the k-fold cross validation, splitting it on 5 and giving the answer. So it will do it, and the grid search CV will return you the best fit line the best fit line, and you can see we executed this, and the grid search CV made the whole changes for all the alpha, which tried for all the alpha which it can do, and now it gave you a whole most accurate line that it can provide with the data, which with the alpha values which you give. Now if you want to see what is out of all the alpha values it tried, which is the best one for our model, so we'll execute two functions, which is regression, the regression function that we made, regression dot best params underscore best underscore param score. So best parameter, where it will tell you the exact parameter for which the best value is found out. So alpha is equal to 100. So out of all the values that you provide for alpha, the best parameter that you got is for alpha is equal to 100. And what is the best score that we got? Now the score will depend on what scoring you're providing it. It's mean squared error. We're trying to find out the mean squared error. Now the mean squared error we have is minus 29. As you can see, the very first time we made it for linear regression, it's minus 37. Now it's minus 29. Now it means it's ridge regression did what? It made our model accurate, more accurate as compared to normal linear regression. The same thing happens in Lasso. I'll not take the next Lasso. The same happens in Lasso. We just write instead of grids, we write Lasso, provide the alpha values. We use the grid search CV. CV is equal to 5. We try to fit the line and we put the parameters, the best parameter score, best parameters and the best score. For this, the alpha value is equal to 1, gives you the best answer, and the answer is minus 35. As you can see, both the answers, the ridge and the lasso, will be better than the linear regression. So that's what ridge and lasso do. And this is the only the answer which I printed for actual and the predicted. You can check it out again. So that's today's class, guys. I hope you understand. If you have any doubt, put it in the group chat or the Slack. I'll put this particular notebook also. Search for it, like go through it again and again. If you have any doubt, put it in the class, put it in the